So here is the plan of the talk. So I'll start with imperfect recall games and then get into some details. The goal being mostly to kind of invite you into this topic rather than throwing all the technical details. So here is the model. Okay, so it's going to be games on trees. Okay. So we have two players, max and min. And along with max and min, there is a chance player to denote probabilistic moves. Okay. So some of the examples are like, chess, Go, Blocus. These games do not have any probabilistic moves. But on the other hand, Monopoly, Backgammon, where there is a roll of a die, there is a probabilistic move. Now, what is this game tree? So each node in the tree represents a state of the game. So if, for example, if you think of chess, it could be a configuration, a certain configuration of the play. And then from that state, depending on whoever moves, the game goes to a different configuration, right? So that is how the game is. So if you look at it here, so each node is partitioned into three types. It could be a chance node represented by a triangle. It could be a max node represented by this pink circle, or it could be a min node represented by a square. So when it is a minimizer's node, it's minimizer's turn to play. When it is maximizer's node, it's maximizer's turn to play. Okay. Now, how does the play go? So initially there is a probabilistic choice. Let's say the play moves here. Then minimizer chooses something. The play ends here because there's nothing more. And then there is a number here. What is this number? It is the amount that the minimizer pays to a maximizer. Okay, so it's a zero-sum two-player turn-based game. Okay. And technically, this is called an extensive form game with perfect information. Okay, so when we see imperfect information, it will be clear why this is perfect information. Now, for these games, you want to compute certain quantities. So before computing them, we need to say what are strategies for players. Okay, so what are pure strategies? It's just a function from your own nodes to the actions that you intend to play. Okay, so for instance, if I look at a maximizer, so maximizer has three nodes, this one, and this one. And from each of them, he has two choices, A or B. A pure strategy just fixes one particular action from each node. Okay, so it says that from 1 you do this, from 2 you do this, from 3 you do this. Similarly, for minimizer, there's only one node. The minimizer strategy just chooses one particular one particular action from this. Okay. Now, once maximizer and minimizer fix their strategies, you can actually compute a quantity called the payoff. Okay. So what is the payoff given that maximizer plays sigma 1 and minimizer plays tau 1? Let's see what it is. So this yellow is actually sigma 1 and this blue is tau 1. When the game starts here, with 0.4 probability, you go here, and then the maximizer simply plays this. Okay, so this is one outcome. Okay, what is the other thing? With 0.6, you go here, and the minimizer plays this. This is the second play. These are the only two possible plays once you fix the strategy to be sigma 1 and tau 1. Okay, and the payoff is calculated like this. With probability 0.4, you reached 1. So you take 0.4 into 1. With probability 0.6, you reached minus 1. Okay, so you sum those things up. Is that okay? Fine. So what is the quantity of interest? So in this case, for this talk, we will be looking at max-min strategies. So once you fix sigma and tau, you know what is P of sigma tau, right? So you want to compute the max over min. As in, once maximizer chooses sigma, minimizer will give a best response. Okay, knowing that minimizer is going to play the best response, you want to maximize your strategy. This is the max-min strategy. Okay, and this is what we will be looking at throughout the rest of the talk. So in this case, max-min or min-max doesn't matter in these kind of games, but later in the kind of games that we will see, they will be different. So that's why I'm just fixing it to be max min for the rest of this. Okay. So in this game of perfect information, how do you even get this max min strategy, max min value? It is quite simple here. You just need to do a bottom up search. So for instance, at this node, there is no reason for maximizer to take this, right? Because once he does that, the payoff will be -10. So the maximizer will just do this. Now this means that the amount of money that you get here is 1. Now at this node, the minimizer has to choose between -1 and +1. So minimizer will naturally choose the -1. Okay. So at every node, you just do a bottom up, compute values at every node. And depending on whether you're a maximizer or minimizer, you determine what to take. Okay, this is a simple bottom up linear algorithm. Now, let's talk about something which will be important, which is the notion of behavioral strategies. See, in a pure strategy, you just decided to take either A or B. In a behavioral strategy, you just simply associate a probability to every, at a node, you have a choice, you associate probabilities to each of them. You have a probability distribution along your. So in this case, I chose 0.2 here, 0.8 here, 0.9 here, 0.1 here, and so on. So once both the players choose their behavioral strategies, the resulting game will simply have numbers along every edge. It will be probabilities. Now, how do you compute the expected payoff now? It is like for every leaf, you just take a product of the numbers, multiply by this value. For this leaf, take a product, multiply by this number and so on. So given a behavioral strategy for each player, we have an expected payoff, a number associated. Okay, good. Now, once again, the quantity of interest is max over all behavioral strategies, min over behavioral strategies of minimizer, expected payoff. Okay, fine. So here is one point. Do we actually need this randomization in this case? We don't need. See, if you're at you're making a choice and you know that if you do this, you will get this value. If you do this, you will get this value. And you are either a maximizer or minimizer. There is no need to randomize. You just do the best possible. Okay. So when optimal values after the actions are known, randomization is unnecessary. So in this case, as we said, we just do a bottom up and that is the end of story. Okay. So here is the first checkpoint. So far, we have seen what are perfect information games and this idea of max-min strategies. Okay, this is where we are.
So under what sort of situation this max-min will be the same as the min-max? Here
it will be.
Yes.
Later, we will see that it will not be like when we look for.
But there can be more generic setting also where the max-min will be the same as min-max.
Yes. Even in imperfect information, for certain kinds of imperfect information, you will have max-min to be equal to min-max. Okay, so now we are going to start thinking about imperfect information games. So where does this imperfect information come from? Okay, so consider a card game. So max and min are there. Max receives one card from spade or club. Okay, and min receives one card from heart or diamond. Okay, so what are the states of the game? States are all these combinations. Okay, one card of max, one card of min. But from Max's view, suppose Max gets the spade. Max does not know whether it is the heart or the diamond for min. So in Max's view, these two states are equivalent, right? So Max cannot distinguish between these two states. Max cannot distinguish between these two states. This is the imperfect information. Okay, Max knows that he's in one of these two states, but not exactly which one. Okay. So here are some examples. So now we'll look at some abstract examples. Okay, how do we denote an imperfect information set? Imperfect information game. So without this red bubble, it's a normal game that we just saw before, extensive form game with perfect information. This bubble is called an information set. The point is that Max cannot distinguish between these two nodes. Okay, and we will be calling it an information set. Now, suppose, see, you see that the actions out of these two have to be the same. It cannot be C, D here and A, B here, because these two are the same, so they should have the same outgoing actions. Now, should Max play A or Max play B? Okay, this is a question, right? Now, if Max plays A, okay, see, you know that with 0.3 probability you will be here, with 0.7 probability you will be here. Okay, now if Max plays A, okay, here there is nothing that Max gets. Here Max will get 1, so the payoff will be 0.3. On the other hand, if Max plays B, with 0.7 you get this one, right? So Max will play B. Okay, so far so good.
Sorry, I missed this thing. Why is it the case that the outgoing actions from all these vertices have to be the same? I mean, it could
Yeah,
have
see,
been-
because you cannot distinguish between these two nodes. So to you, it's like the same signal that you get, and on receiving that signal, you have to play some actions.
Yeah, but I could have played, let's say, here there is a C, there is a D there, and then I could have,
No,
I mean, I don't know where I am, but like I know these are the set of available actions.
no, they
So
may
you
not
can-
even be legal moves, right? I mean, if the actions are different from here, just saying that these two are the same, you may not
You
even
were
be
saying
able
that if the actions are different, then I can actually
see that there.
distinguish them.
Yes, yeah,
Okay, by seeing what are the outgoing
Correct.
actions and somehow
Yeah.
that is a distinguishing.
exactly. So now made a small change here. See, previously this was a chance node with probability, right? But now I've made it into a minimizers node. So it's not like, I mean, there's probability with some probability you come here, with some probability you come here. This you cannot say anymore. Okay. So let's see. Suppose Max plays A. Remember that we are interested in the max min value. Okay. If Max plays A, the best response of min would be like to go here. Okay. Because then the overall outcome will be 0. The payoff will be 0. Right. Now, if Max plays B, min will play L. Once again, it is 0. Now randomization starts to make sense. Okay. So Max will not play just A or B. So Max will try to randomize. Let's see. Suppose Max plays A with 0.25 and B with 0.75. Okay. What should min do? Okay. So min knows that if B is played with 0.75 and its the lower probability is on A. So let me do left so that the payoff is just 1 still. Okay. The best response of min is still a pure strategy. Okay. So in general, if Max plays A with X and B with 1 minus X, min will do this decision. Oh, is X less than 1 minus X? Then you do L. Otherwise, you do R. And whatever you do, the answer will be min of X comma 1 minus X. That will be the payoff. You see, are you with me? Right? So knowing that min is going to do this, Max will choose an X such that X equals 1 minus X. Because if X was less than 1 minus X, let's say 1 by 3, then the payoff will be 1 by 3. So Max will decide to just keep X equal to 1 minus X. So that is the payoff here. Okay. And the strategy is to play A and B with half-half probability. So it's not, I mean, this is just to illustrate that it's not always half-half. So for instance, if A, after doing A, you get 2, and after doing B, you get 1 here. Okay. You apply the same kind of reasoning. This and this will be just yielding 0. Now, I want to do this with X and I want to do this with 1 minus X. See, if you play X, the payoff will be 2X. Sorry. It's 2X plus 1 minus X. Right? Now, if 2X is less than 1 minus X, min will just do this. Otherwise, min will do this. And so the maximum is attained when 2x equals 1 minus x, and this gives x equal to 1 by 3 as the as the behavioral strategy. Sorry, yeah, as a behavioral strategy. Okay, good.
Yes, sorry, maybe I missed this. So in this case, the max player does not get to see the moves of the min player.
Yeah, because we are calculating the max min strategy.
Right, but if the min player supposing chose L,
Then it will be a min max.
I see. Okay.
Yeah. So for some reason we have made this choice. Okay.
I see.
So I can complicate it further, but the point is the same. I mean, see, so here there are two information sets. Okay, I'll just tell you in an abstract way what you don't need to go through the. So there are two information sets here. Here there are two choices. Here there are two choices. Let's say that at O1, Max can play X and 1 minus X. Whereas here it is Y and 1 minus Y. Okay, because at each place you can choose with different probabilities, right? And then what happens? The payoff will be XY here, whereas here it will be 1 minus X into 1 minus Y. And in some sense, minimizer is minimizing between these two, depending on what your X and Y values were. And knowing that, it is better for Max to just play something where X equals 1 minus X and Y equals 1 minus Y. Okay, we can match. Come in, sorry?
No, if you want to equalize X, Y, and 1 minus X, 1 minus.
Yeah.
I mean, like in the first information set, if Max chooses B, and in
Okay.
the second it chooses A always.
Okay.
Oh, Max is Max. I'm sorry. Yeah, it's the other. Sorry.
Yeah. Okay. Good. Yeah.
You just get it confused.
Very good. So, okay. So this is fine, right? Like,
Yeah.
good. Yes. So, I mean, again, once again, you will end up with X equal to half, Y equal to half, and maximum will be 1 by 4. X into Y. Okay.
So this is a specific strategy that you have.
No, I'm
set
saying.
A, I mean, so at theta 1 with probability X, you choose A, and theta 2 with probability Y, you choose A. So this is the
This is a strategy,
this is
right?
a strategy.
Where X could be anything from 0 to 1. You have to find your X.
Yeah. Okay.
There is something else here because, okay, I agree that the player does not see the node inside the information set, but he does see that he played X. So can he say that if I played X and it turned out to be A, then I'll do something. If I played X and it turned out to be B, I'll do something else for Y.
See, what happened is, I mean, we'll come to this somehow. See, once the player, I mean, how do I say this? So, when you are at O2, you simply receive a signal O2.
You don't have history that I did something.
No, you don't, because, I mean, we will come to that. Okay. So, this is something related to what your strategies cannot like alter the structure of the game somehow. Like, you see, I mean, we will do something called recalls. Maybe when we come there, we will understand this. Now, here is one thing where the point of this example is to say that sometimes your behavioral strategies may even require irrational numbers. So the optimal probabilities could be achieved at irrational values. Okay. So there's something just let's remember this. It will be helpful in So this is another type of imperfect information where, see, when you are here, you even forgot that you received the same signal. Okay, so you can think of this bubble as a signal that you receive. Okay, so initially the game starts here. The player receives the signal, let's say O, and then the player has to choose between left and right. Okay, now suppose the player chooses left. Now, once again, the player receives the signal O. Okay, so this is called an absent-minded driver because it's like, so you are at an intersection. You can either go left or right. You went left, and then you're again at an intersection, but you forgot whether you were at the previous intersection or this intersection. Everything looks the same to you. Okay, so this is that kind of an example. And in this case, what is your behavioral strategy? Let's say. So by the way,
So
this
signal is the same as an observation. When you say signal,
yeah,
it's the
is
same as an,
yeah.
okay.
This typically happens when you have parking which is in basement. So you forget whether you did one U-turn or a couple of U-turns when you're in basement 2 or basement 3. So it's indeed an absent-minded driver example. So anyway, so yeah, so here you see, I mean, how do you associate the payoff? Whatever probabilities you associate here, it should be the same. Because the strategy associates to every signal, whether you play, I mean, an x and a 1 minus x. Okay, and when you do that, you get all these complex polynomials. Okay.
Sorry, how did you arrive at that? Like, if you could quickly
Ah.
say-
Yes, yes. See, I'm saying that my behavioral strategy
Mhm.
is like I'm going to play x, I mean, I'm going to play left with probability x and right with 1 minus x.
Mhm.
Since this is the same signal,
Mhm.
from here again, I have to put x and 1 minus x here.
Okay.
You agree?
Okay,
Right? Now we compute.
I see.
You reach this leaf with
Okay.
x square, you reach this with x into 1 minus x, and this
four.
is 0. Okay, so that's what gives you
I
this. So there's a second checkpoint now. Here we are, which is that remember perfect information, imperfect information. In the imperfect information, you need behavioral strategies, you need randomized strategies. And the point is that the optimal strategies may require irrational numbers. Okay. So what is the complexity of max-min computation? In the sense, given a game and given a lambda, is the max-min value bigger than or equal to lambda? This is the decision problem. Yes. So when in order to do that, within imperfect information, you have to like make further hierarchies. It will not end here. I will make more hierarchies, but for the moment, we have two different kinds of hierarchies. Okay, I mean, two different kinds of games. Okay, this is based on the nature of the imperfect information. So let me. So this is an important slide. Okay, so look at this example. So if I look at, so for instance, if I look at this node, it is a maximizer's node. Okay, what has the maximizer played so far? Nothing. This is the first time maximizer is playing. So its history is epsilon. Here also the history is epsilon. Okay. Now what about this node? How does the maximizer reach there? As in, it is after doing, I mean, epsilon, I mean, after doing O1 dot A. And then you come to O2. Okay. What about this? O1 dot A dot O2. Okay. Similarly, if I do this, this will be O1 dot B dot O3. This will be O1 dot B dot O2. Okay.
Why not just O1 dot B? Why did you?
Yeah, it doesn't matter. O1 dot A, O1 dot B, doesn't matter. Okay, it's going to be the same anyway. Yeah, let's just get rid of this. Okay. Now, you see, in some sense, when the player receives O2, it cannot distinguish where in O2 it is, but the player remembers her sequence of actions when she came here.
Mhm.
Okay, so the player knows that I received O1 and after that I played A and that's how I came here. Okay, whereas look at this. So here there is an O1 dot A and here there is an O1 dot B. Okay, so player has forgotten. So and both of them are in the same information set, which means that player has forgotten whether she played A or B. Okay, see everything has an O1, so at least she knows that I was at O1 before, but I do not know whether I played A or B. Okay, which means that she cannot recall her own actions. So this is called an imperfect recall. Okay. Now this is, you see here.
Is there a third model where you have O1 with two states and then you play A from both and now they're in different sets. So you gain some memories.
Yeah, this is in principle allowed. The information sets allow it. Okay. Yeah, but what it means is a different thing. Yeah.
What it will allow that from if one has three states
Mhm.
and among any two, both of them lands in the same state in O2. If we allow that.
This is okay. You can allow it.
Means those are not two different states and not in a single red bubble that we cannot distinguish. I'm saying it's only one state.
I think this is similar to this question. So you're saying that you were in one information set. After playing an action, you came to two different.
No, he's saying it's the same information set, but two nodes lead to the same inside the information.
This is possible. Yes. It is. I mean, like you're saying something like, I'm here, and then there is something that came like this, and there is something else that came like this.
No, to the same.
Same.
No, but this is a tree, right? So you will have only
I
one.
understand.
Huh.
In tree that is not possible. If you allow that, so why do we change?
Oh, like if you assume a DAG like thing, I mean the complexities will in principle change. I do not know what happens because it will be more succinct, and I do not know what. That's a good question.
Yes, sir. When you have here chosen the first picture,
Hmm.
while you have taken the probability model, triangle, and use that, all of them has to have same outcome 0, 1, 0, 1, 0, 1, 0, 1. In the first picture, the first graph.
Okay. So you mean the probability distribution?
Yes.
That's because I was talking about pure strategies,
Yes.
right? And then you can also have behavioral strategies, which is where you randomize. See, a pure strategy is a special case of a behavioral strategy where you just give 0 or 1. Okay. Good. So let me quickly.
But you showed that the mean player always has a
best response. The best response. See, because once you know what the max has played, there is no imperfect information for you. You know the optimal things. So it's like you just do a bottom up. Okay, sorry. So here is the last thing. See, if you look at this, what is the history here? It's just, I mean, if I put an L here, and this is called an O, it's O dot L. You see, within O, you have a node whose history talks about O. That means the player has forgotten whether she received the same signal before. Okay, then this is like a further level of imperfect recall. It's called absent-mindedness. Okay. Yeah. So here are the known results, which is notice that these are all imperfect information. Okay, and within that you have perfect and imperfect recall. So for perfect recall games, so you have imperfect information, but still you recall. You can build a linear program to solve the max min. Okay, and it can be done in P time. For the others, so if you look at the one player case, you can show that, I mean, in this case, when it is not absent-minded, pure strategies suffice. So you just need to guess a pure strategy. Okay, so that puts it in NP. And apart from that, it's not known to be NP hard. Okay.
Suffice for what?
No. To find the maximum value for this. Okay. And in the general two-player case, it was known to be NP hard even without absent-mindedness. Okay. So what are the
So
results?
for the one player case, then there's no min. There's just one player and nature, or
Yes. Yeah. So what are we going to do is we are going to look at some better complexity results, let's say, okay, for these things based on the first order theory of things. So what is this first order theory of things and so on? So first, let's just look at this. What is this? This is just an inequality. You have some variables, real valued variables, x on x1, x2, and y, and this is just a polynomial inequality. Now, what is this? This entire thing? It's a Boolean combination of inequalities, right? And on top of that, you add quantifications. This is first order theory of things. Okay. If you just have a conjunction of inequalities, I mean, it's like there exists X, Y, so on, so such that all of them hold. That's like just the existential theory. And on top of that, you can have quantification for all quantifiers. Okay, so this is more formally, these are the things that are allowed in its syntax. Now, consider this decision problem. Suppose you are given an existential sentence, that is, there are no other free variables in this file. Okay, there exists some variables.
So what would be second order?
There exists for all. Oh, no.
Second order
You mean second order theory.
Calculations.
Okay. There you
Calculations.
have, oh, I see. So here you have variables which range over reals. There you will have variables which range over sets of reals. Okay, that will be the second order variant.
Also, the constants that are allowed are only integers. Right?
Yeah. Yes, you are. Okay.
So the constants are allowed are only integer.
Or algebraic numbers, because that you can define any variable.
Exactly. Yes. Okay. So, and then, so this is the decision problem. So given something like this, okay, you can think of it as satisfaction of polynomial inequalities, conjunction of polynomial inequalities, okay? And is it true? Okay, does there does. And the complexity class is called there exists R. It consists of the set of all problems that can be reduced to this problem using a polynomial time reduction. Okay.
So explicitly, all of first order theory is equivalent to existential. No?
No.
Okay. So
What do you mean? Like,
so if I have exists for all exists and all,
okay.
can I do those quantifiers?
Yes.
Can reduce to
Right.
existential? So
Yes.
Explicitly, I think.
Correct. You're right. Okay.
Complexity might change maybe.
Correct. You're right. So that's the thing. So, so this class was introduced as a complexity class in this very, very nice paper. Okay, and then they showed several problems that you can they established ingredients that you need to show reductions from existential theory of reals to your own problem. Okay, and several other problems have been shown to be lying in this complexity class. Typically, when the answer is an irrational number, it smells of existential theory of reals or there exists for all. Okay. So you can extrapolate this. I mean, what is the complexity class? There exists for all. It is similar thing, but with with an alternation of quantifiers, one alternation. Okay, and as Subhash said, this can be, there is a quantifier elimination method which can reduce it to there exists. And so as long as it is bounded quantifier, I mean, when you look at a bounded quantification, all of these fall under P space. Okay, because of this result. Good. Yes. So I hope you have a perfect recall of what we said before. So this is where we were, and here are the results. So what we did was, in the absent-minded case, we could show type bounds using these classes. So in the one-player case, it is there exists are complete, and in the two-player case, it is there exists for all are complete. Okay, and in addition, when you are not absent-minded, when you are just, I mean, you don't your information sets do not cut across yourself. It was known to be NP hard before. It was known to be NP hard. We additionally showed it is square root sum hard. Okay. So, but no one knows what it just strengthens your thought about the problem. Let's say. I will. So, given a bunch of numbers A1, A2, AN, positive number, non-negative numbers, and a P is square root of A1 plus square root of A2 plus square root of dot AK less than or equal to P. Okay, this is the square root sum problem. Its complexity status is open. So it lies somewhere within P space, I believe. But what is it? It's whether it's an NP, it's not.
You just have to sum all of them. You don't have to take a subset.
No,
Just sum all of them.
sum all.
It's about the numerical.
Yes, exactly. Good. So let me just give you an idea of the upper bounds, and so there are like 2 or 3 main ideas. The first idea is that essentially checking for behavioral strategies can be reduced to checking for manipulations over polynomials, right? So that's the first step.
So, sorry, what is the, which setting you are here, you are that accent minded?
I'm showing both actually. So
And what were the results? Could you?
Yes, yes.
So you have, okay, existential.
So I'm saying that how does it fall under there exists are, I have to give an existential statement,
Yeah.
right? And the point, this is that existential statement. That's what I'm trying to say. Okay, because since you want only behavioral strategies, you just write the polynomial
Yeah.
and ask, does there exist X such that this? And for the Y, it is again simple, which is that you write the polynomial, okay, which is this one, but you just need to be a bit careful that you ask there exists x1, x2, such that for all y, as long as my x1 and x2 is between 0 and 1 and y is between 0 and 1, if that is the case, is this inequality true? So just because of that extra for all quantification. Okay.
So, sorry, there you say something like max mean greater than equal to lambda.
Yes.
So you don't.
This is max min only. See, what does max min mean? So if I give you an
You were
x,
talking about max mean only.
yes, 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 yes. So no matter what the minimizer chooses,
Yeah, sure.
I want to ensure this, that no matter what translates into a for all quantification. Okay. So let me just briefly tell you about the other way, the hardness. So if I give us an existential sentence, how do I convert it into a game? Okay. And where is absent-mindedness coming into picture? Okay. See, suppose I have a polynomial. This is given to you. Okay. I'm going to construct a game out of it. So there are 4 monomials. Okay. So I'll start with a nature node and I'll put 4 edges out of it. Okay. Now this subtree should be taking care of 3x square. I essentially need to get x square, right? So I'm going to put 2 nodes with x and 1 minus x, x and 1 minus x. So in order to have the same value, I'll put this and this in the same information. Okay. And here I get this, I mean, essentially 4 into 3. That is what I get. And once again, for this one, I just have to put x and y. And this x is the same as this x, so I put this information set. I mean, wherever x appears, I will put the same, I will cover it using an information set. Okay, that kind of. So this will give you an immediate reduction from polynomials to games. Okay, and then we make use of some existing result, which is that deciding if a system of quadratic equations has a common root in 0, 1 is known to be their x's are complete. See, one thing is that all these x's and y's that we have in the game, they are all in 0 and 1. So the polynomial that you have before may not necessarily have values in 0 and 1. So you need that one step of, and thankfully they have done this on 0 and 1. So from there we could reduce it. Yes, this is for. Now what about 2 players? So this thing is known to be there exists for all are complete. Okay, so you may wonder about the. So the results appeared in 2020, but this result appeared in 2024. We couldn't have predicted this result, but so actually when we wrote the paper in 2020, we did not have this bound. Okay, because there was something some really fundamental missing. Like essentially we did not have this. So we had to do something around it. So we could show their exists are hard and for all are hard for the 2-player version. But we could not show there exists for all are hard. Okay. But last year, they showed that this problem is there exists for all are complete. And from there, we could kind of immediately get what we wanted. Because previously, these 2 proofs that there exists are hard and for all are hard required some heavy lifting. But all of them has been absorbed into this lemma. So we outsourced it there and we get a reduction. Okay, good.
So here the, I mean, the main thing about this lemma is like when an event if the x's and the y's are
Are
restricted
bounded.
to this bound,
Yes, yes.
then also it's
Yes.
this for all are complete.
Yeah, so there is this paper which deals with all kinds of variations where what if they are open intervals, what if they are closed intervals, and so on, and results vary. Okay, and thankfully for the variant that we wanted, it works. So, okay, fine. Yes. So lastly, what about the non-absent-minded case? So here you see, whenever we do a reduction from the polynomial, you need that absent-mindedness. You need this this kind of thing.
Mhm.
Okay, otherwise you cannot get x squared. Okay. Whereas in the non-absent-minded case, the polynomials that you get will be multilinear polynomials. No x will repeat again. Okay. And here it was known to be NP hard, and we showed square root sum hard. This is the problem. Given positive integers, decide if root a1 plus root a2 blah, blah, blah is less than or equal to 3. Okay. And the main challenge here was to construct a game whose maximum value is minus root n. I'm not going to go into the details, but this was the challenge. Okay, so we have kind of given you a glimpse of the complexity. So let me quickly do this polynomial time fragment. So just to put it in perspective, so if you look at imperfect information games, here on the bottom you have perfect recall for which you have polynomial time. Here in the very top you have absent-minded things for which you have these complexity classes. And in between, so there is some square root, some hardness, which I didn't put, but there is this white area. Okay, so this was the topic of the second paper where, yeah, further distinctions within here. Okay, so we need to kind of zoom inside a little bit more. Look at these two games. Okay, now this is the first time Max is playing. So here all the histories are epsilon, epsilon, epsilon. Now what about this? So all these are in one information set. So you see there, I mean, if I give O1 here, this will be O1.h, O1.t, O1.h, O1.t, and so on, O1.h and O1.t. You see the lack of information is only because of her own actions. She remembers O1. Okay. So this is one kind. Whereas here, there is an O1.t and an I'll call this O1 and this O2. O2.h. Both of them lie in the same information set. Okay. So we are going to make a distinction between these two. Okay. This one has already been given a name. Okay. It is called a loss recall. I mean, so it's called action loss. This is the name that is there. And what is known about it, see, it was defined as early as 95. That one player A loss games can be solved in polynomial time, almost like perfect recall games. Okay. And in the two-player case, if the minimizer has an A loss recall, then it can still be managed in polynomial time. Okay. Not the other way around, because if it is like this, if it is a maximizer is A loss and minimizer is perfect recall, then it is square root sum hard, as we showed. The reduction that we had actually resulted in an A loss recall player. Okay.
So when you say one player, you also don't have the nature.
No. Nature is always there.
Nature is always
Always
there.
there. Okay. So let me just. Okay. So this is the augmented picture. All this is prior work. Okay. We have a p time here. But still, what about this?
And your imperfect recall setting always talked about A loss, or was there like previous slides?
No, that's what. See, previous slides,
You had
absent-minded was there. That is like the very high end.
yeah.
Okay. And then there was one extra result about the square root sum, which actually resulted in an A loss recall.
Okay.
Like somewhere here, it's just above perfect. Okay, so that's the. So let me quickly tell you two results now. So we gave a new class called shuffled ALOS. Okay, I will tell you what that means. And it still results in polynomial time algorithms. Okay, and the second result is that, see, there is this white part. We showed that every game in this white part can be converted into an ALOS game. Okay, but mind it, we have to be careful. This place is NP hard. This is polynomial time. Okay, but we say that everything can be converted. So there should be somewhere you pay, right? So in general, this can give an exponential blowout. Okay, but it has a simplified information structure. Okay, here it can be a very complicated imperfect. So it's like you have a small game. Okay, you can either run an exponential time algorithm on this game, or you can convert it into a potentially exponentially large sized game on which you can run a polynomial time algorithm. Okay, so it's so this is the, at least the result is this reduction. Okay, so what is shuffled ALOS? I will just maybe I'll just quickly illustrate. I don't think I'm so in this game, if you can see, this doesn't have ALOS recall because this information set and this information set, both of them feed onto this. Okay, so this does not have ALOS recall. But on the other hand, if you shuffle the actions, you try to do A, and after that you try to do B and C. Okay, it turns out that you get the same polynomial finally. See, here you get, if you put behavioral strategies, it will be XB, XA plus XB, XA bar, and so on. So if you look at the polynomial for both, it will be the same. However, this has an easier information structure obtained by shuffling the previous game. Okay, and when you can actually do this, we say it is called a shuffled ALOS. Of course, the challenge here was, if I give you a game, I want to detect whether a shuffle of it will give you ALOS, and we show that it can be done in polynomial time. Okay, you cannot just keep doing all kinds of shuffles. I'm not going to get into the details. And finally, what is this other thing that I said is that, look at this game. In fact, we can show that using an algorithm that even on shuffling, you will not have ALOS recall. But there is something called, if you look at the polynomials that you get, this is XA, XC, XA, XE bar, and so on. There will be polynomials here which can be combined to get this. So I just look at this yellow thing. This is A C bar. If you look at this, it is C bar D A plus C bar D bar A. So when you do that, D plus D bar will give you 1. And you will finally just get A C bar. Okay, so the point is, each leaf monomial can be obtained as a linear combination of some monomials of this game, of the second game. Okay, and then we say that the second game spans the first game. Okay, and it turns out that for every game, you can find a span which has ALOS recall. Okay, that's the, once again, I'm not getting into the details. And we can also give a family of examples exhibiting the blowout. Okay, so one last slide. What I did not say and what is there is that you can also have an algorithm to compute the minimal span. It could be exponential in the worst case, but you can compute a minimal span. And all these shuffled ALOS in this business can be extended to 2-player games. Okay, that's it. So here is a summary. I will actually show a picture. Okay, so this is a summary of the talk, which is, this is what was there. Okay, and there are 3 things to take away, which is that this NP hard has become this one. Okay, in the first order theory of reals. This ALOS has become a bit more. There's a shuffled ALOS coming in, which is also P time. And finally, the middle portion is not left out. You can say something about it, which is that anything here can be reduced to an A loss game, albeit it could be a bit bigger. Okay, so somehow we have tightened the picture about imperfect recall games. Okay, so this is the overview. And what next? So these imperfect recall games are used as abstractions of perfect recall games in many algorithms, like and with significant reductions. So we are wondering how these new kind of polynomial travel time fragments, how do they influence the algorithms is one thing. These two in approximation algorithms, I mean, I do not know, like if suppose I'm happy with an approximate answer for maximum strategy. Okay, so we have not looked at that. And also parameters. Are there some sensible parameters to be looked at for which we get, FPT algorithms and so on, based on information structure? And finally, other solution concepts. Nash equilibrium. What about instead of the non-zero sum case, what about Nash equilibrium? Okay, that's it. Thank you for your attention.
Where would some games the right side is a integer or what is it?
Yeah, yeah.
Does it become harder or do you know anything about it if you change it to algebraic number or something?
I don't know. I don't know. Yeah, is there anyone who knows more about square root sum here? I know whatever I know is there on the slide. So
There's something called cube root sum here.
I don't know. Is people study cube root sum problem?
I haven't seen that.
Yeah.
I don't know.
More questions?
Okay, if not, then let's.
Thank you.